All right, today we are getting into the one force that basically runs the entire universe, gravity. We're going to explore how we can actually calculate that massive pull between stars and planets, and it all starts with this surprisingly simple idea of point masses. So let's just jump right in. I mean, have you ever really thought about it? What is this invisible cosmic tether that holds our planet on this perfect path? Keeping us from either spiraling into the sun or just flying off into the void. It's a question that stumped some of the smartest people in history for thousands of years. And the answer, it turns out, is this single, beautiful law that connects the biggest things you can imagine with the smallest. The same force that choreographs gigantic galaxies is the exact same one that makes an apple drop. See, there aren't separate rules for up there and down here. It's one law, and it is everywhere. So to really get a grip on this cosmic dance, we've got to go back, way back to the 17th century and the brilliant mind of Isaac Newton. He's the one who finally put all the pieces together with one single elegant law. And that brings us to our first big idea, a universal attraction.
So what does this formula actually mean? Well, it tells us two really simple but powerful things. First, the bigger the objects are, the more mass they have, the stronger their pull on each other. You double the mass, you double the force. Simple. But second, and this is the really cool part, the force gets weaker the farther apart they are. And it gets weaker fast. It's called the inverse square law.
Now, you might be thinking, hang on, that formula says point masses, but we're talking about giant planets. And this is why it works. Newton figured out that for something like a planet, you can pretend its entire enormous mass is all squeezed down into a tiny single point right at its center. It's a brilliant shortcut that makes the math way, way easier without losing any accuracy. Okay, so we've got the rule book. Now let's actually use it. I mean, it's one thing to see a formula, but it's something else entirely to use it to measure the unbelievable power of the cosmos. It's time to calculate some cosmic forces. And trust me, we're starting with a big one. So let's tackle our own solar system. We know the Earth is locked in orbit around the sun, but how strong is that connection, really? What's the actual number in newtons that keeps us from flying away? Well, let's find out. To solve this, first we gotta gather our cosmic ingredients. We've got the mass of the sun and the Earth. These numbers are so huge we have to use scientific notation. We've got the distance between them, and here's a super important tip for any physics problem. Make sure your units all match up. That's why we have to convert the distance from kilometers into meters, so it plays nicely with our gravitational constant, g. And now for the fun part. We just take that slick formula and plug in all the massive values we just collected. This is it, theory meeting reality. We're multiplying the constant by the two masses up top and then dividing the whole thing by the square of that insane distance. And the result? Whoa. It's just staggering. That's 3.6 times 10 to the power of 22 newtons. We're talking about a 36 with 21 zeros after it. It's a force so big, it's basically impossible to compare to anything on Earth. It's this immense, silent, invisible tether stretching across 150 million kilometers of space, holding our entire world on its perfect path. That's not just a number, that's the strength of our solar system. So, okay, we've got this gigantic force, but why does that make us go in a circle? Why doesn't it just yank the Earth straight into the sun? It's a fantastic question, and it leads us right into our next section, gravity's perfect circle. Just look at this diagram. The planet is moving sideways, right? It has velocity. And because of inertia, it wants to keep going in a straight line forever. But gravity is always there, constantly pulling it inwards. The result of this perfect, non-stop tug of war between moving forward and being pulled in is an orbit. The planet is literally always falling toward the sun, but it's moving so fast sideways that it always misses. And here's the key idea, the real mind bender. In a stable orbit, the gravitational force is the centripetal force. They're not two different things fighting. They're two names for the exact same force. Gravity is what provides the inward pull, that centripetal force, that's required to keep something moving in a circle. And once you realize their formulas are equal, you can unlock the secrets to how any orbit works. So if we know the rules of the game, can we actually engineer an orbit for a specific job? Oh, you bet we can. And it's led to some of the most amazing technology we have. Let's look at a really special case, the geostationary satellite.
A geostationary satellite is so cool because, from our point of view, it just looks like it's hanging motionless in the sky. But to pull off that trick, you have to follow a very strict recipe. 3 things have to be perfect. First, its orbit has to take exactly 24 hours. Second, it has to be moving in the same direction as the Earth. And third, it has to be right above the equator.
And why do we care so much about this? Because this isn't just abstract physics. This is the tech you use every single day. Your GPS, your satellite TV, global phone calls, weather forecasts, a lot of that is powered by satellites that stay perfectly locked over one spot on the globe, all thanks to these precise rules of gravity.
So how do engineers find this magical sweet spot in space? Well, they use the exact same principle we just talked about. They start by setting the gravitational force equal to the centripetal force. Then it's just a bit of algebra to solve for r, the orbital radius, and once you have that distance from the Earth's center, you just subtract the Earth's radius itself, and boom, you've got the satellite's altitude.
And here they are, the magic numbers. To stay geostationary, a satellite has to be at a super-specific altitude, about 35,900 kilometers up, and be blazing along at over 3 kilometers a second. If it's a little too high or low, or a little too fast or slow, the whole thing's off. It's an incredible display of precision engineering.
Okay, that was a pretty deep dive, from planets to satellites. So let's lock in the most important ideas with a quick review to make sure this all really sticks.
All right, a quick conceptual check. No big numbers, just the relationship. Forget everything else for a second. If you just take 2 objects and double the distance between them, what happens to that gravitational force? It gets 4 times weaker, right? Because the distance is squared on the bottom of the formula. So if you double the distance, you're dividing by 2 squared, which is 4. That's the inverse square law in action. It's one of the most important rules in all of physics. Okay, next one. This one's a little easier. What if you keep the distance the same, but you just increase the mass of one of the objects? The force gets stronger. It's a direct relationship. More mass means more gravity. If you can remember those 2 basic ideas, more mass means more pull, but more distance means much less pull, then you've totally got the core of Newton's law down. And for a final thought to leave you with, Newton's law works between every single pair of objects in the entire universe. So right now, as you're sitting there, you're being pulled down by the Earth, of course, but you're also being pulled just a tiny bit by the moon, by the sun, by Jupiter, even by the most distant galaxies. All of those little tugs add up to a net force. You're at the center of this invisible cosmic web of pulls. Kind of wild when you think about it.